Okay, few questions about cosmology and astronomy. So look at this first question. Question is, energy level En of the hydrogen atom are described by the empirical equation. En is equal to minus 13.6 electron volt over n square. This n is the number of the orbit, number of the energy level. Calculate the energy in joules of the photon of the ultraviolet light emitted when electron in the hydrogen atom falls from energy level 1 to energy level from energy level 3 to energy level number 1. So first we will calculate the energy of third energy level. This is 13.6 electron volt divided by 3 square. So after calculation, it is coming approximately 1.51 electron volt. Then energy of the first orbit, first energy level is 13.6. You can ignore this negative sign. 1 square, so it is 13.6 electron volt. Now, energy is actually the difference of energy of two energy level. So the difference of these two energy level is 13.6 minus 1.51. And this is coming 12.1 approximately per electron volt. And then we will convert this in joule. Do remember, 1 electron volt is 1.6 into 10 power minus 19 joule. You have to remember this. So the difference of the energy in the energy of the electron in the hydrogen atom, sorry, energy of the photon is 12.1 times 1.6 into 10 power minus 19. So after calculation, it is coming 1.94 into 10 power minus 18 joules. So this is the answer. Next is calculate the wavelength of these photons. So the energy is equal to HF or HC over lambda, because V is equal to F lambda. So speed of light, F lambda, and F is equal to C divided by lambda. So energy is 1.94 into 10 power minus 18. The Planck constant H is 6.63 into 10 power minus 34. The speed of light is 3 into 10 power 8 divided by lambda. So the wavelength is 6.63 into 10 power minus 34 times 3 into 10 power 8 whole divided by 1.94 10 power minus 18. And after calculation, the answer is 1.07 approximately into 10 power minus 7. So the next part is the hydrogen spectrum is observed in the light from a distant galaxy. It is found that the wavelength corresponding to an electron in the hydrogen atom falling from the energy level N3 to energy level 1 has increased to 1.25. Look, initially it was 1.07 times 10 power minus 7. Now it is 1.28. Explain why this increase takes place. Okay. So due to the Doppler's effect, source of wave moves away from the observer, wavelength increases. So in this case, the galaxies are moving. As the galaxy is moving away from our Earth, and we are observer, we are standing on the Earth, thus the wavelength is increasing due to Doppler effect. So this answer. Next, calculate the speed of the galaxy relative to the Earth. So the formula is change in lambda over lambda is this change of speed over speed of light. Mean we can write V is equal to delta lambda over lambda times C. Then V is equal to the change of both lambda from 1.07 to 1.28. 1.28 minus 1.07 whole times 10 power minus 7 divided by the actual wavelength is 1.07 into 10 power minus 7 multiply the speed of light 3 into 10 power 8 10 power 7 cancelled. So this the change in the velocity is coming approximately 7.3 into 10 power 7. So you have to use the value here, maybe 1.03, I think so. So if the answer is, your answer is coming 1.03, then do use here the 1.03, okay? So you have to use this answer over here. Next, the C part is, explain why the changes in the wavelength such as this have lead to the idea that the universe is expanding and to a Big Bang theory. Look, according to the formula, V is equal to H naught D. So this is a recessional velocity and this is a distance. It means this recessional velocity is directly proportional to distance, mean all galaxies are receding from our Earth. So the receding velocity h directly proportional to distance. So when the distance is increasing, the recessional velocity delta v or the v is also increasing. But when we will go back in time, going back in time, galaxies must have been closer to each other because the recessional velocity is equal to h naught d. So in the previous time, all galaxies were very close to each other. And then long enough, when we will go back long enough time, all galaxies must have been at the same place. And this is the evidence, or this is known as the Big Bang theory. So I repeat, recessional velocity is equal to h naught d, delta v, recessional velocity directly proportional to d. All galaxies are receding from our Earth. The distance is increasing, so the recessional velocity is increasing. But when we'll go back in time, all galaxies must have been closer to each other. But going back long enough time, all galaxies must have been at the same point, and this is the Big Bang theory. So this is the first question. Okay, the next question is, define for the star the term luminosity. So this is total power radiated the surface and it is measured in watts. And the luminous flux means the intensity. So this luminous flux is actually the intensity of radiation at the distance of the star like absorbed, received by Earth in the power per unit area, receiving at a certain surface from the distance from the star. Next, all the information gained by the astronomer about the star, apart from the sun, is gained from their electromagnetic radiation. Describe the principal information gained from the color of the star. So definitely, the color of the star will give you the temperature of the star, I mean the surface temperature of the star. So surface temperature of the star will be determined from the color and the absorption spectrum of the star. So this absorption spectrum will inform about the element present on the star. Element present at the star and also inform the speed of recession of the star. So these are the two informations. Number one, the element present at the surface of the star, and number two, the speed of recession of the star is observed from the absorption spectrum. Next, a green spectral line viewed in the lab has a wavelength of 516.7 nanometer. The same spectral line viewed in the radiation from the distant galaxy has a wavelength of 543.32 nanometer. Calculate the velocity of the recession of the galaxy. So V recession velocity is delta lambda over lambda times C. This is the formula. Now, the difference of these two, 543.2 minus 516.7 and times 10 power minus 9 nanometer divided by the actual 51.6.7, 10 power minus 9 into speed of light, 3 into 10 power 8. So when we will cancel this, and then the difference of this is coming approximately 26.5. So 26.5 times 3 into 10 power 8 divided by 516.7. The answer is coming 1.54 into 10 power 7. This is the recessional velocity. Next, estimate the distance of the galaxy from the Earth. The Hubble constant is given 2.3, 10 power minus 18. So we will use the formula V recession velocity is equal to Hubble constant times distance. So the distance is equal to recessional velocity over Hubble constant. So D is equal to 1.54 into 10 power 7 divided by the Hubble constant is given 2.3 into 10 power minus 18. Yes, it's given in the seconds. No need to change it. But the speed is also in seconds. So the distance will be approximately 6.7 into 10 power 24. So this is another question. And the next question is, the surface temperature of the sun is 5800 Kelvin and the light from the sun has a maximum intensity at the wavelength 520. Light from the star emits a maximum intensity of the wavelength 480. The luminosity of the star is 4.8 10 power 29. calculate the peak surface temperature of the star. So according to Wien's displacement law, lambda 1 T1 is equal to lambda 2 T2. So here the peak surface temperature is required for which wavelength? The 480. So 480 times T1. And this wavelength is 520, definitely 10 power minus 9. Here minus 9 cancelled. So no need to write. 10 power minus 9 both sides cancel. And the temperature is 5800. So the temperature will be 520 into 5800 divided by 480. And after calculation, the answer is coming 6,280. And the next is calculate the radius of the star. So the formula is luminosity is equal to 4 pi sigma Stephen Boltzmann constant, then r square and T power 4, fourth power of the temperature. This is the formula. And this radius is required. So we will write r square is equal to L divided by 4 pi sigma T power 4. And for the radius, we will take the under root both sides. So R is equal to, the luminosity is given, I think this is 4.8 10 power 29. 4.8 into 10 power 29 divided by 4. Pi value is either 3.14, 22 by 7. And the Stephen Boltzmann constant value is 5.67 into 10 power minus 8. And times the temperature is 6280, it's power 4 and whole under it. So let me calculate. 4.8 10 power 29, 4 into this. So approximately this is coming 2.08 into 10 power 10 meter. So this is the radius of the star. So the next question is, the Sketchy graph showing how the relative intensity of the light from the hot body varies with the wavelength of the light. So according to Wien's displacement law, it is like this. This is a wavelength, and this is an intensity or a certain temperature. This is a graph. And the next, the sun has a surface temperature of 5800 and the wavelength of light of the maximum intensity after at the wavelength of 520. A distant star has the wavelength of the maximum intensity at the wavelength of 210. Calculate the surface temperature of the distant star. So again, the Wien displacement law at the lambda max is inversely proportional to temperature. Our lambda 1 T1 is equal to lambda 2 T2. So initially, temperature is this. It is 5800 and its maximum wavelength is 520 times 10 power minus 9. And then the wavelength is 210 into 10 power minus 9 per the nano, and temperature is required 10 power minus 9 cancelled. So this temperature is equal to 520 times 5800 divided by 210, and after calculation, it is 14,400. Wavelength and temperature both are inversely proportional to each other. And the next, using the data from the similar star, it is estimated that the surface area of the distant star is 6.3 into 10 power 17. From your answer, calculate approximately the luminosity of the star. So look, Stephen Boltzmann's law is luminosity is equal to 4 pi sigma r square T power 4. And then luminosity is equal to 4 pi r square. So this is the surface area. Sigma T power 4. And the luminosity is equal to area, Stephen-Boltzmann constant, T power 4. Now the question is luminosity. So the luminosity is equal to the surface area is 6.3 into 10 power 70 meters square. And the Stephen-Boltzmann constant is 5.67, 10 power minus 8, and the temperature calculated is 14,400 power 4. And after calculation, this power 4, then power. Okay, so the answer is coming 1.5 into 10 power 27. Next is the intensity radiation incident on the Earth from the distant star is 1.6 into 10 power minus 9. Estimate the distance of the star from the Earth. So inverse Kerala, look, flux intensity is equal to luminosity divided by 4 by d square. So we can write then d square is equal to L divided by 4 pi f, and then taken the under root, we can calculate the distance. Luminosity is given here. It is 1 point something. Yes, 1.5 into 10 power 27. So put the actual value. It was 1.54 into 10 power 27 divided by 4. Pi value 3.14, and the flux intensity is given 1.6 into 10 power minus 9 and whole under root. This will give you the answer for the distance. The calculation, this is coming approximately 2.75 into 10 power 17. Okay, next question is a star known to be a distance of 3.80 into 10 power 17 meter from the Earth. It provides a spectrum of light as shown in the figure. So this is brightness and the wavelength graph. Use Wien's displacement law to determine the surface temperature of the star. The constant probability of the Wien's displacement law is 2.9. So look, the maximum wavelength is equal to constant divided by temperature. And this constant is given here. So we have to calculate the temperature. It means the temperature is equal to the Stephen's constant, this Wien's displacement constant divided by lambda max. This is 2.90 into 10 power minus 3, and the wavelength is mentioned here. It is 582 into 10 power minus 9, and after calculation, the answer is coming approximately 5,000 Kelvin. Next, this star provides an intensity of the radiation at the Earth's surface. This is the flux intensity. Calculate the radius of the star. Okay, this is 4-mark question. So we will use first flux intensity is equal to luminosity divided by 4 pi d square. So the luminosity is equal to flux intensity times 4 pi d square. So first luminosity, this flux intensity is 2.38, 10 power minus 8, multiplied by 4, multiplied by pi 22 by 7, and the distance must be given. Yes, it is 3.8, 10 power 17. So it is 3.8, 10 power 17. So the luminosity of the star is coming approximately 1.81 into 10 power, 1.81 into 10 power, I think 36. Okay, I missed this scare here. So the answer of the luminosity is coming. It is 4.32 into 10 power 28. Then we will use the formula. Luminosity is equal to 4 pi sigma radius square t power 4, radius required. So R is equal to L divided by 4 pi sigma t power 4 under root. Now substitute the values. 4.32 into 10 power 28 luminosity divided by 4. This is 3.14. And then Stephen Boltzmann constant is 5.67 into 10 power minus 8 multiplied by your temperature 5000 by power 4 and then whole under root. Calculate. So it is 4.3. Yes, it's coming approximately 9.9 into 10 power 9 meter. Okay, the next question is, a star is observed from the Earth. The Earth is a distance of 6.04 10 power 6.04 10 power 18 meter away from the star. State the name of the term used for the cosmologists to describe an object of the known luminosity that is used to determine the distances of the star. So definitely it is standard candle. Next is the light from the star that is observed from the Earth is found to be redshift. Explain what is meant by redshift. So redshift is increase in the wavelength of light when source moves away from the fixed observer. The Doppler effect. State what can be deduced from the observation about the motion of the star. So from the motion of the star is this a formula. So this formula is showing that this recession velocity is increasing due to the redshift. It's moving away from the Earth. The star is moving away from the observer, away from the Earth. And the next part is explain how the observation of the redshift may in many galaxies has led to the Big Bang theory. We have done in the question number 1 again. So the redshift is showing that the recessional velocity is increasing with the distance, but going in the past, all galaxies were close to each other, but the recessional velocity was small. So this leads to that in the past, there was a point from which all are originated, and that is called the same point or the singular point. So I repeat, delta V is inverse as directly proportional to D. In the past, all galaxies were close to each other. Delta V was small, distance was small, but in the past, they were the part of the same point, mean they were originated from the same point, and this leads to the Big Bang theory. Okay.